Hello, lovely humans. Jen Foxbot here for another edition of STEM Bites, where we tackle your seemingly simple questions about science, tech, engineering, and math. All right, here we go. I'm very excited because we have another wonderful question from our dear friend Mama Llama. Here's Mama Llama. She's here to ask a question today. Yeah. Okay, Mama Llama, what you got for us? Well, my dear, I'm very curious about derivative calculus because I love math. Yeah. Wait, I want to know what is acceleration? No, derivative calculus. Acceleration. No, derivative calculus. Acceleration. Ah! Wait, my friends. It's okay. We can cover both at the same time. Two two hands, two puppets, two questions. Here we go. Okay. Oh, right. Okay. I crack myself up sometimes. Anyway, yes. What is derivative calculus and what is acceleration? I think that understanding some of the mathematic concepts that can be a little tricky can be helpful to pair them with a real world situation. So, both Science Squirrel, who's curious about acceleration, and Mama Llama, who likes mathematics and wants to know more about derivative calculus. Let's get into it. Okay, so for our example, we are going to draw a lovely graph. Yay, pictures. So we are going to draw a graph. And maybe if I'm plan ahead in my brain a little bit, we'll move our graph over because we might draw more than one graph. Okay, so we have our handy dandy graph, and on the bottom axis, we have time. The horizontal axis, we have time. And on the vertical axis, we have distance, which I'm lazy and I'm gonna write distance. And because most of the world uses the metric system, we're gonna use kilometers today. So we'll make some little tick marks to make it more easy to see our plot. And so the units of distance are kilometers and the units of time are hours. So we'll just say, okay, 1, 2, 3, 4. 1, 2, 3, 4. Okay, so let's say that we are riding our bicycle along, or maybe we're walking. We are taking our sweet time. And so every hour we move 1 kilometer. So that means the first hour that we're walking along, we go 1 kilometer. By the second hour, we have gone 2 kilometers. Maybe we are a tortoise, or maybe we just stop and smell the roses and enjoy our sights. By hour 3, we have gone 3 kilometers. And by hour 4, we have gone 4 kilometers. And then we are like, all right, I'm at my friend's house, I'm done, or whatever. So that means that we are moving kind of at this like straight line. Sorry, it's a really bad line. Okay. And we can represent this motion, we can represent our walk with an equation. So you might be familiar with the, let's use some colors here. With the equation y equals mx plus b. So this is the equation for a general straight line. We are going to translate this into our particular situation. And so in this case, y is your vertical axis. It is your your dependent variable. Basically, what happens on the vertical axis depends on what's going on here. And for us, humans, we can't really control time. It's a little bit out of our control. But you know what we can control? Distance. How far we walk, or perhaps how fast we walk, where we walk. If we walk, if we want to go up or down or left or right, back and forward. Up is a little hard sometimes. So that is our dependent variable. So in this case, I'm going to use x. I hope that's not too confusing, but it'll be a little bit more clear why I'm using x. For distance, you can also use d. It's a variable, which means you can vary what it means. It's a placeholder, a stand-in. And the m is going to stay the same. The m is our slope. And in this case, our independent variable, the thing that's out of our control, is time. And b is the interception. And in this case, it's 0. So now we can do our algebra to figure out what our slope is. But basically, what you would do is it's just rise over run. So how much your line rises over how much it moves over. And so then I didn't quite use my colors how I was anticipating, but that's okay. We'll make it work. So the distance traveled can be represented by rise over run. And in this case, it is 1 kilometer per 1 hour. So the rise is 1 kilometer every 1 hour times our variable t. And if we wanted to be even lazier, we don't need to write the 1 in the bottom because 1 divided by 1 is 1. So that is our equation. Heck yeah. So let's say we wanted to predict where we would be in 6 hours. We can just plug in the amount of time to calculate our distance. So we'd be like, if I were to walk for 6 hours at this slow, leisurely pace, I would be 6 kilometers, because 6 hours times 1 kilometer per hour, the hours cancel and you get 6 kilometers. Cool? Easy peasy. All right, so y'all are like, yeah, no problem. Where does the calculus shenanigans come in? Here we go. Okay, so what if we want to talk about speed, how fast we're going? Our intuition is like, 1 kilometer an hour is hilariously slow for a human, perhaps, depending on who you are. I walk pretty fast. I definitely walk faster than this. So for me, my intuition is like, well, this is pretty slow, but like, how slow? Well, we can calculate that using derivative calculus. So speed is actually a rate of change. It is how much our information of interest is changing. And this is, for me personally, a way I like to use time in real world scenarios, because this really means like how much is our distance changing over time. So speed is the rate of change. Okay. And in calculus, we can represent that by saying dx over dt. And what this really means is how much is our variable of interest. Oh, actually, let's use these colors now. So our variable of interest, our dependent variable, changing over time. So in this case, you can actually think of the operator in calculus as d dt. How much is our particular variable changing over time? And in this case, our variable is distance. But you could have all different kinds of variables changing over time, right? You could have sound waves changing over time. You could have, this is where I'm blanking on all of the examples. You could have color changing over time. I don't know. Yes, anyway, so again, arbitrary variables, and in general calculus and pure mathematics, you're not necessarily going to just be dealing with time. Any equation can have a rate of change. Okay, and the variables are just to like connect it to the real world to make it a little more tangible. Okay, so then we can calculate the rate of change of our equation here. And so we would take the calculus operator and we would apply it to this equation. And so we would say, okay, what is d dt of our equation for distance? So we just plug the equation for x into here and we say 1 kilometer per hour times t. And what we get is just 1 kilometer per hour, because that's how the operator works. There are certain rules in calculus that you kind of just need to remember, which is annoying. I am not a huge fan of memorization. I'm a huge fan of understanding things and understanding why it works the way that it works. But basically, you can think about this intuitively by saying, okay, well, the rate of change is the slope. Okay? The slope is showing you how much your line is changing over time. And so you really wouldn't necessarily need calculus to calculate the rate of change of a line, because you can just look at it and say, okay, well, I know that every kilometer I go 1 hour. Every kilometer, it's been an hour. Every kilometer, it's been an hour. And so you can say, okay, that means that my rate of change or my speed is 1 kilometer per hour. Okay, so you don't necessarily need to do calculus. However, that analysis is the same thing that calculus allows us to do, but calculus makes it easier to extend to more situations, which we will see in just a sec. So, and that just a sec is right now. Haha, okay, here we go. Okay, so we are going to make another plot. We will have time on the on the horizontal axis. It's not an x-axis right now. We have time in hours, and on the vertical axis, we are going to put speed. Yay. Speed. Okay, and then I'll make my tick marks so that we can plot this. And so if our speed is just 1 kilometer per hour, well, hey, it's constant. Our speed is not changing. That's it. So whenever we check in at some time in the future, assuming I'm still taking my leisurely stroll 8 hours later, which maybe I am, I've walked that long before, then it doesn't matter what time we check in, I am still going the same speed. And now we get to Science Squirrel's question, which asks, well, what's the acceleration? What is that? Acceleration is the rate of change of our speed, or how fast or how much our speed is changing. So acceleration would be represented, la 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 la, I need more chalkboard space. Okay, so acceleration, and I'm, again, you know me, I'm lazy, so I'm going to write ACC for acceleration. So if we are looking at the rate of change of speed, then that means we are actually taking our operator and we are operating it on speed. But what is speed? Well, we've already taken the rate of change of distance. So that would be d dt on dx dt. Boom! Hey! We just got to second derivatives. So the acceleration is actually the second derivative of distance. In other words, it is the rate of change of our speed, and speed is the rate of change of our distance. Super cool. So in this case, we can look at our straight line and say, well, wait a second, we're not accelerating at all because our speed is constant. It's not changing. Boom. Yes, exactly right. Viewer that was thinking and subconsciously, telepathically transmitted your question. So in this case, the acceleration is 0. And you can see, because if we were to take the derivative of a constant number, it's constant, it's not changing. So that's just 0. That's acceleration. Okay, so we have gone pretty thorough through this basic example. We will end with a more complicated example, which actually does have a rate of change of speed, aka has an acceleration component. So bear with me for a few more minutes and we will cover that, and then we will wrap up and you'll be like, oh, I understand derivative calculus. At least that's my hope. And acceleration. Sorry, Science Squirrel. I hope that it helps you to understand both. Okay. So let's say you went on your walk and you're like, that was so slow. I want to move faster. Yeah, I get it. I get it. Okay. So now we're still in distance in kilometers because metric units are great. Okay, we might run out of space. Okay, so let's say that we want to go a lot faster, and so at 1 hour we are we are at 1 kilometer, but we're like, this is way too slow. I need to pick up the pace. And so by 2 hours, you are at, hold on, I need to do some math in my head. Whenever I get put on the spot, I'm like, oh, math in head. I work much better on paper. I can do a lot of mental math, but sometimes I get like deer in the headlights type thing, which is okay. It happens. Okay, hold on. I guess I'll spoil it. So we are going to use a parabola. So x equals t squared. So at hour 1, we can just plug this in and calculate. Then 1 squared is 1. At hour 2, 2 squared is 4. So by hour 2, we are at 4 kilometers. By hour 3, we are at 9 kilometers, which is not that, but pretend with me. Okay, so we are moving fast. We're like, all right, no time for appreciating the scenery. I'm late to a meeting with my friend, or brunch with my friend, so I gotta book it. Okay, so in this case, the rate of change of our distance, or speed, is dx dt, and that equals 2t. So you bring the exponent down, and then you multiply it by your variable. We're not going over the rules of derivative calculus, just what it is and what it actually means. So we'll punt that for now. This is just something that you get used to with enough practice. And the rules aren't that complicated once you get them down. And they start to kind of make sense, because if you look at our parabola, you can double check that by being like, what is the rise over run? Okay, well, check this out. So at first, we move 1 kilometer per 1 hour. Okay, that's easy peasy. That was the same as last time. But wait, for the second hour, we move 1, 2, 3, 4 per 1 hour. Okay, so now all of a sudden our rate is doubling. And for hour 3, we move from 4 to 9. So we move 5 paces over 1 hour. And so you can check this by just taking the amount of time that you have gone and plugging it back. No, okay, hold on. We'll skip that part. Let's draw speed. I'm confusing myself at this point. Okay, let's draw the graph for speed, and that will help us to visualize how this is different than our straight line. Okay, so you have time and you have speed, which I'm going to keep there because I'm lazy. If I had been smart, I would have not erased the whole graph, but that's hard to do. Okay, so in this case, whoops, I swapped colors this time. Well, here we are. Okay, so speed is 2 times time. So at time 0, we haven't gone anywhere. Our speed is 0. We haven't started moving. At hour 1, we are at 2 kilometers per hour. So, oh, and I guess I should just specify this is kilometers per hour because it's speed. So at the first hour, we have gone to 2 kilometers per hour. At hour 2, 2 times 2 is 4. So 4 kilometers an hour. At 3, we're at 6, somewhere up here. And if you connect these, you'll notice it is a straight line. Hey, what up? So yeah, because 2t, and then you could say, well, plus 0. That is the equation of a straight line. However, it's not constant. We have a rate of change here. So we have a rate of change that is 1, 2 over 1, 1, 2 over 1, 1, 2 over 1. So in this case, the acceleration is 2 kilometers over 1 hour time, well, 1 hour squared. And so we would take the derivative to double check that, I suppose. So d squared x dt squared, and that is just going to equal 2. And since we're doing real units, it will be 2 kilometers per hour times, 2 kilometers, yes. Kilometers per hour squared, or Yeah, hours squared always looks funny to me because I'm so used to meters per second squared. Anyway, so our acceleration is 2 kilometers per hour squared, which means that for every hour, we are doubling our speed. And if you're like, what does that mean? Well, you can just say that we are accelerating and our speed is changing. The end. There is acceleration, so therefore our speed is changing over time. And that's it. I hope that was clear. I got a little sidetracked by my by the stories in my head sometimes. So I really hope that was helpful. Please let me know if you have any questions about derivative calculus. Again, I want to stay focused on, what it means and what it actually what it does versus like memorizing the rules and stuff. I do know that this can be a little tricky, like actually taking the derivative. Um, there's lots of resources online. Wolfram Alpha is really great. You can always look these things up. So that's where I would prefer to answer questions around like the logic of it and the meaning of it, because I think that that is much, much harder to look up. Although it's getting a lot easier with tools like AI. So you can help get explanations for these types of things using your favorite AI tool. But you do have to double check that because AI is not always correct. Okay. Thank you very much for watching. Please let me know if you have any questions about science, tech, engineering, and math, and I will see you next time, my friends. Goodbye.